Okay, in the last class, we started to discuss point groups. And first we discussed low symmetric point groups and then high symmetric point groups. We've so far considered the point group TD and the point group T. In the last class, we have already begun to discuss the point group OH. So we have seen that in the point group OH, we have a C4 axis as the principal axis. So the C4 axis rotates the object around a 90-degree angle, and we have overall three C4 axes. So this is a general property of a high symmetry point group. We have multiple principal axes present. We also saw how many symmetry operations are associated with these axes. So now, in addition to that, we have C3 axes, and these C3 axes, they go to two opposite triangular faces of the octahedron, and they rotate the triangular faces by 120 degrees, and after that, the object superimposes again. So how many of these do we have overall? We have overall 4 of these. That is because, well, each C3 axis passes through 2 opposite faces. We have overall 8 faces in our octahedron, so we have 8 over 2 is equal to 4 C3 axes. And overall, we have 8 operations associated with this. So we have 4 C31 and 4 C3 2. So the C3 is equal to the identity. Okay. What's next? Well, we also have C2 axes, and these C2 axes are actually C2 primes because they are not conjugate to the C2 axes that we have seen before, which were the ones that are exactly in the same position as the C4 axes. So instead, these C2 axes, they go through the center of 2 opposite edges, as you can see here. And we can, of course, rotate by a 180-degree angle, around that axis, and afterwards our octahedron superimposes again. So how many of these C2 axes do we have? So we realize that each C2 enters the octahedron through the center of an edge and leaves the octahedron through the center of an edge. So how many edges do we have in our octahedron? So we have overall 12. We can just count them in order to verify this. We have 1, 2, 3, 4. Then we have 6, 7, 8, 9. Sorry, that's not correct. So we have 1, 2, 3, 4. And then we have 5, 6, 7, 8. And then we have these 4, 9, 10, 11, 12. So therefore, we would have 12 over 2 is equal to 6 of these C2 prime axes. Now, how many symmetry operations do we have? Well, for C2, we only have the C21 operation to consider, because the C22 operation is producing the identity. For that reason, we have now also 6 C2 prime 1 symmetry operations. Okay, so now we have covered all our proper rotational axes. So next we can go to the mirror planes. And they are both horizontal as well as vertical mirror planes in the points for each to consider. Let's turn our attention first to the horizontal mirror planes. And you see one horizontal mirror plane here. And you see that one horizontal mirror plane contains 1, 2, 3, 4 edges. So as we carry out the symmetry operation associated with this mirror plane, okay, we'll move, well, these two vertices around, so they just switch up their position. The remaining vertices, these 4, 1, 2, 3, 4, they do not move because they are part of the horizontal mirror plane. So why is this a horizontal mirror plane? This is a horizontal mirror plane because this mirror plane stands perpendicular to one of the 3 C4 principal axes that go through 2 opposite vertices. Namely, it's actually the axis that actually goes through this vertex and that vertex. Note, though, there are also principal axes that contain this mirror plane. That would actually be this one here. Okay. And the other one, however, well, so to say, the horizontal properties trump the vertical properties, and we consider this mirror plane a horizontal mirror plane. So how many of these would we have? Well, you see that each mirror plane contains 4 edges. Okay. Remember, we have overall 12 edges. So we would expect 12 over 4 is equal to 3 of these mirror planes. Okay. Now you see the other mirror planes here. So this is the one that we already considered. Okay. So the second one is actually here, is actually in plane with this square here, made of these 4 edges. And the third one actually stands here. You see, it is actually containing the plane made of these 4 edges. So how many symmetry operations are associated with these mirror planes, given that we have 3 sigma h mirror planes? That is pretty straightforward to answer. Can any one of you perhaps do this? How many operations do we have to consider? How many operations are there per mirror plane? That's one answer in the chat. 2. Yeah, that's actually not correct. So when we can, well, we can reflect and we can reflect back. But when we reflect back, we are producing the identity. Okay. Therefore, we are not considering the second operation, the back reflection, so to say, but only the original reflection, the first reflection. So for that reason, we only have 1 reflection operation per mirror plane. So we have overall 3 mirror planes. Therefore, we need to consider 3 reflection operations. Okay. Now, in addition to these horizontal mirror planes, we have vertical mirror planes, which are dihedral mirror planes because they bisect the angle between two C2 axes. And you see one horizontal, one of the dihedral mirror planes here. Okay, so now you see that in contrast to the horizontal mirror planes, they do not contain four edges. Rather than that, they actually bisect two opposite edges, this one and this one here. Okay, and they're going through two opposite vertices. Okay, so now because of that, this kind of mirror plane does not stand perpendicular to any principal axis. Okay, therefore it has no horizontal properties. However, it contains one of the three principal axes. This mirror plane in particular contains this C4 axis here. Okay, therefore clearly we would consider it a vertical mirror plane. So however, this vertical mirror plane also has the property that it bisects the angle between two C2 axes. Okay? Namely this one here and this one here. Okay, you see clearly that the angle between these two is bisected by this mirror plane, and that makes this mirror plane a vertical mirror plane. So how many of these vertical dihedral mirror planes would we expect? Can anybody maybe make a educated guess? Again, it's useful to consider the Platonic solid properties of the polyhedron in order to derive the number of dihedral mirror planes. Okay, there is a suggestion. 3. So let's see if this is true. Okay, so there are actually 6, and you see them actually all here. So how can we understand that they are 6? So we have these two opposite edges that are basically cut by this mirror plane. Okay, so overall we have 12 edges to consider. So we have 12 over 2, which is equal to 6 mirror planes. Okay. Yeah, there's a question. David, what is your question?
Yeah, so my question is about the slide before and this one. So since the mirror plane in the slide we already, yeah, the horizontal, yeah, it's, I think it's going in the same direction as the principal axis. So why did we say it's horizontal? So because there's, like, I know there's a C4 that goes from the top to the bottom, and then there's C4 that can be perpendicular to the plane. So why did we consider this plane to be perpendicular to the C4 axis instead of saying that it goes in the same direction as a C4 and therefore it's vertical?
Yeah, so basically this mirror plane does not only have the properties of a horizontal mirror plane, but also some properties of a vertical mirror plane, because while it indeed stands perpendicular to the axis that goes through these two vertices, right? It contains actually the other two C4 axes that goes through these two. Yeah, these two and these two. Okay, but by definition, horizontal properties trump vertical properties, and so the mirror plane is considered a horizontal mirror plane because of that reason.
So it has the properties of both?
It has the properties of both because it stands perpendicular to the first C4, okay, while it contains the other two C4 axes. Okay, but because it stands perpendicular to at least one of the three C4 axes, it's considered a horizontal mirror plane. As opposed to these that only have the properties of a vertical mirror plane. They do not stand perpendicular to any of the three C4, but they contain one C4. Therefore, these mirror planes only have vertical properties, so therefore they have to be considered vertical.
Okay, yeah, this makes sense. Thank you.
Okay. So now, since we have 6 vertical mirror planes, we also have 6 operations associated, because again, we have always only one reflection operation per mirror plane to consider. This is always the case when we have a mirror plane. All right, so what other symmetry elements do we have in the point group OH? So we also have an inversion center, and that's pretty easy to see. It's just in the center of our octahedron. And as we carry out our symmetry operation, well, we just move all points through the inversion center to the other side. Okay, we can just do this. Okay, and you see that the polyhedron that results superimposes the original one. So how many inversion centers do we have? Well, we can have never more than one inversion center. And there's also only one symmetry operation associated with one inversion center. That is because carrying out the inversion twice produces the identity. Okay, so this is pretty straightforward. Now we also have rotation reflections, which are not as straightforward. And we have here S6 rotation reflections with S6 improper rotational axes, and you can see that these axes stand perpendicular to two opposite triangular faces. This one here and this one here. Okay, and they go to the centers of these two opposite triangular faces. Okay, now because they are improper, there must be also a mirror plane perpendicular to that, an improper mirror plane, which stands here perpendicular to this S6 axis. So how are the points in the object being transformed? So in this case, we just rotate around 60 degrees, and then we mirror at the mirror plane. And then you see that our polyhedron superimposed. So the reason why we can rotate around 60 degrees and then mirror is essentially because these two triangular faces, okay, they stand in a in a staggered orientation relative to each other. So when we rotate around 60 degrees and then reflect, this triangular face here will superimpose this triangular face here. And as a consequence of that, all other points in the object will also superimpose. So now, how many of these S6 rotation reflections will we have? Now you see that these S6 improper rotational axes stand exactly where the C3 proper rotational axes were. They were also going through the center of two opposite triangular faces. So for that reason, the number of S6 symmetry elements is the number has the same number as the C3 symmetry elements. So these were overall 8/2. That's 4. That's because we have 8 triangular faces. Okay, so the S6 goes to 2 opposite triangular faces. And therefore we have 4 of these. All right, and you see them all here. So now we again need to determine how many symmetry operations do we have. So now you see our improper rotation reflections have an even order. That means that we have to consider basically everything from S61 to S66. However, S66 is the identity, so that takes away the S66. So now it is, however, the case that an S62 is equal to a C31. That is because when we reflect 2 times, then that is the same as not reflecting at all. So we basically only rotate 2 times by 60 degrees, which is the same as rotating by 120 degrees. For the same reason, the S64 is equal to a C32 because we again reflect an even number of times, which is as though we do not reflect at all. And rotating 4 times by 60 degrees is the same as rotating 2 times by 120 degrees. So in addition to that, an S63 is the same as an inversion, because of which the S63 is also not an independent symmetry element. So for that reason, we only have the S61 and the S65 as a unique symmetry operation. And because we have 4 improper rotational axes, we have 4 S61 to consider and 4 S65, which gives overall 8 S6 rotation reflection operations. Okay. Then in addition to the S6 operations, we have also S4 operations to consider. Now the S4 improper rotational axes, they go through 2 opposite corners of the octahedron. That means that they stand in the same positions as the C4, but they transform the coordinates or the points within the object in a different way. Okay, that is because the 90-degree rotation is followed by a reflection perpendicular to the S4. So in detail, this works like the following way. First we rotate, but then also we reflect. So now how many of these S4 operations will we have? Well, we would expect that we have the same number as for the C4. For the C4, we had 3. And so for the S4, we would expect the same. Okay. The first one goes to these two opposite vertices. The second one goes to these two opposite vertices. And the last one goes to these two opposite vertices. Okay. So now how many operations will be associated with this? So in principle, we would consider everything between, well, S41 and S44. We know that the S44 will need to be the identity that leaves the S41, the S42, and the S43. So now it turns out that the S42 is also not an independent symmetry element. Can anybody explain why? Can you see to which other symmetry operation S42 would be equivalent or identical? Yeah, there's a suggestion. E, where the identity would be reflected by the S44. Okay, so the S44 is the same as the identity. But what about the S42? Okay, S42 means that we are carrying out the S4 symmetry operation 2 times. So if we carry out the symmetry operation 2 times, which is the angle we rotate about overall? Would that make a reflection? No, unfortunately not. So we rotate 90 degrees 2 times. So around which angle do we then rotate overall? (180) exactly. So now we also have to reflect 2 times. Okay. So now reflecting 2 times is the same as what? So it's the same as not reflecting at all, okay? Because reflecting back and forth produces the identity. So that means that if we consider the rotations, we have rotated around 180 degrees. If we have, with regard to the reflections, we have just done nothing. That means that we have actually only rotated by 180 degrees. Now that would be equivalent to what symmetry operation? A C2. Yeah, correct. So it's the same as a C2-1 symmetry operation. Okay, so overall, we would only consider the S41 and the S43, but not the S44 because that's the same as the identity, and also not the S42 because that's the same as a C21. Okay. All right. So now we have considered all the symmetry elements and all the symmetry operations that we have in the octahedral point group. Okay. So we have the identity, an inversion, we have 4s6, we have 4c3, we have 3s4, we have 3c4, we have 6c2, 3c2, 3 sigma h, and 6 sigma d. And you see again here listed all the associated symmetry operations. Okay, so this is just a summary of what we just worked out. So that's already quite a lot of symmetry elements and symmetry operations. However, there's another platonic solid which has even more symmetry elements and symmetry operations, and that's the icosahedron and the dodecahedron. But before we go to that, I also wanted to say that there's again a rotational subgroup to this high symmetry point group OH, and that's the subgroup O. Okay. So again, this subgroup is called a rotational subgroup because it contains all the proper rotations of the point group OH, but does not contain all the other symmetry elements. Okay, so it does not contain any improper rotational axes. It does not contain any mirror planes. It also doesn't contain an inversion. Okay, so we have the same symmetry elements as for the point group O, but not the inversion, not the S6 rotation reflections, not the S4 rotation reflections, and also not the mirror planes. Okay. So here is just an example for a molecule with a rotational, belonging to the rotational subgroup O. So this is actually the core of a polyoxymetallate cluster, V6P8O24. And you see it still contains the C4, the C3, and the C2 proper rotational axes, but all the other symmetry elements are gone. Now, when you carry out symmetry operations, then the C4 axis will actually rotate this object by 90 degrees, and then you see it superimposes. So now we can also rotate around the C3, which actually stands here and goes to this phosphorus atom. And you see we rotate now by a 120-degree angle, and our object superimposes. And last but not least, we can also rotate around the C2. And then you see that we rotate here by 180 degrees, and our object superimposes. So we still have our proper rotational axes, but no other symmetry elements. They are all gone. Okay. Well, there's actually another a subgroup to the point group OH, which is called the point group TD. Also, this point group has the symmetry elements of the point group OH, but some of them are omitted. So which ones are omitted? In particular, the C4 principal axis is gone, but the C2 axes are still there. You see actually here a molecule. This is actually a hexa pyridyl iron 2 complex cation, which has an iron in the center and 6 pyridyl units around. So these 6 pyridyl units, they coordinate to the iron in an octahedral fashion. Okay, so indeed the 6 nitrogen donor atoms in blue here, they surround our iron, well, octahedrali. But nonetheless, the symmetry of this molecule is not OH, which is basically induced by the planar nature of the 6-membered pyridine ligands. Okay, so that takes out the C4 axis, but still leaves the C2. So we can rotate this molecule around the C2. Okay, and now it superimposes. So now, in addition to the C2, we also have the sigma H here. That is also still present. But we also have a C3, and that's the same C3 that we had in the octahedral point group OH, and we can also rotate around this one. Okay, and now you see you can rotate around 120 degrees, and the molecule superimposes. So we also still have the F6 that are in the same position as the C3. And you see now as we rotate by 60 degrees, and then we reflect at the improper reflection plane, our molecule superimposes as well. Okay, so overall, we see that the identity, of course, remains, the S6 remain, the C3, the C2, and also the sigma H. By the way, also this inversion center is still there. Yeah, but all the other symmetry elements are gone, namely the C4, the S4, and the 6C2, as well as the sigma D. Okay, so you may wonder if this point group is being derived from the point group OH, why does it get the letter T, which reminds you of the point group PD, which was tetrahedral? That is actually because, like the point group PD, we have 4 C3 axes as the principal axes. Okay, but while we in the point group TD do not have a horizontal mirror plane, we have that in this point group, and therefore we call it TH. Okay, in the point group TD we have dihedral mirror planes, whereas in this point group we have has horizontal mirror planes. So this is how this point group actually relates to the tetrahedral point group TD. There are also relationships to that point group as well. All right. Now we are really done with the octahedral shape, and we can now go to the 2 remaining platonic solids, which have an even higher symmetry with even more symmetry operations. That's the icosahedron and the dodecahedron. So the icosahedron, remember this from last class, is made of 20 triangular faces, and the dodecahedron is made of 12 pentagonal faces. So despite they are made of different polygons, they have exactly the same symmetry and belong to the same point group, namely the point group RH. So in order to derive the symmetry operations in that point group, we could use either the icosahedron as example or the dodecahedron as an example. It would lead to the same result. Okay. So an example, by the way, for a molecule which resembles an icosahedron is the B12H12 cluster. So actually 12 boron atoms that make an icosahedron, and then these boron atoms are bound to 12 terminal hydrogens. And here we have a molecule which is called dodecahedron, which is made of 12 pentagons that are fused together, and each pentagon contains 6 carbon atoms, and see that each carbon atom is also bound to 1 hydrogen atom. Okay, so now let us collect the symmetry elements and symmetry operations for the point group IH, arbitrarily choosing the icosahedron as an example. All right, so again, it's useful to first see what is the principal axis here. And the principal axis in icosahedron is the C5 proper rotational axis. So you can understand this following. You see here that the C5 axis goes actually through 2 opposite vertices of the icosahedron. So why is there pentagonal symmetry? Because you see that this vertex here, which points actually to us, is connected via edges to a pentagon, which is this one here. Okay. And the vertex, which actually on the other side, which points to the back, connects to another pentagon, which is actually this one here. So as we rotate around the C5 axis, okay, we do not move these vertices, but we move all the vertices which are part of the pentagons. Okay, we rotate them by 72 degrees. Okay, now I wanted to animate this, but for some reason the animation doesn't work properly. I hope you can imagine it correctly. Now consider again, our icosahedron is a platonic solid. So that means that each of the vertices is symmetry equivalent. Okay, so now that determines the number of the C5 axes that we have. Okay, so now let's count the number of vertices. So we have, well, these two here, which are opposite to each other. But then we have these ones that belong to this pentagon. Well, that adds 5. And then we have, well, these ones, which belong to the opposite pentagon, which are another 5. So that means we have 2 plus 5 plus 5 is equal to 12 vertices. So therefore, the number of C5 axes is 12 over 2, which is equal to 6. Okay. So each C5 axis goes to 2 opposite vertices within the icosahedron. So now we need to analyze, well, how many operations are there? So now you see that we need to consider every operation between the C51 and the C55. We know that the C55 is the identity, so we need to consider everything between C51 and C54. So these are all unique symmetry operations. The C51, the C52, the C53, and the C54. There's no other simpler symmetry operation which is identical to these. So for that reason, in this case, we have 4 symmetry operations per symmetry element. So that gives, well, 6 times 4, okay, which is equal to 24 symmetry operations, okay? 6 of them are C51, 6 of them are C52, 6 of them are C53, and 6 of them are C54. So now we can check if there are also proper rotations that have a lower symmetry, but C5. And indeed, there are axes, in particular C3 axis. So you see that this C3 goes to the center of this triangular face and leaves the polyhedron to this triangular face. So therefore, we can relatively easily count how many C3 operations we have. So each C3 goes to 2 opposite triangular faces. So how many faces do we have? Well, an icosahedron has 20 faces, so we have 20 over 2. And that makes, well, 10. Huh? You see here all the 10 C3 axes. So how many operations are associated with this? So for each C3 element, we have to consider the C31, the C32, but not the C33, because the C33 is the same as the identity. So that means that we have to consider 2 operations per symmetry element. So that means we have to consider 10 times 2 is equal to 20 operations. Okay, 10 of them will be C31, and the other 10 will be a C32. Okay, so now are there even C2 axes? And the answer is yes. So the C2 axes actually go through the center of 2 opposite edges. Okay, so this particular C2 enters the polyhedron to this edge and leaves the polyhedron to that edge. So again, my animation, oh, now the animation works. I don't know why it sometimes doesn't work. All right, so you see how the C2 rotates the polyhedron. We can again count how many C2 operations we have, and that is essentially determined by the number of edges now. So we need 2 edges per C2. We can therefore count the edges and divide that number by 2, then that gives the number of C2 axes. Let us just do this. Well, we have here these 1, 2, 3, 4, 5. Okay. Then we have 1, 2, 3, 4, 5. Okay. So that gives overall 10. Okay. And then we have in the background the opposite vertex that connects here. We have 1, 2, 3, 4, and 5. Okay. And then we have the opposite pentagon, which gives 1, 2, 3, 4, and 5. So now that gives overall 20, but it's still not enough because now the two opposite pentagons here are interconnected, okay, by additional vertices, and these are these ones here. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. So we have to add another 10 to the 20 that we already have, and that gives 30. So now we have to divide 30 over 2. Well, and that gives 15. And you see now here all the 15 C2 axes. So now how many operations do we have per C2? Well, we have as many C2 operations as we have symmetry elements, because only the C21 is unique, the C22 order produces the identity. Okay, then I see our time is over, and we can just stop at this point.